Can you name the three foundational security objectives behind most controls? Confidentiality, integrity, availability. You may hear them called the CIA Triad. This is not just an interview definition exercise. These three ideas give you a fast way to diagnose security failures, choose appropriate controls, and explain your reasoning to a technical team or a business leader. By the end of this video, you will not only be able to name the three pillars, you will be able to look at a real scenario and ask a better question. Which security objective is at risk, and what control would meaningfully improve it? Imagine a hospital stores thousands of patient records in cloud storage. The files are supposed to be private. But one access setting is configured incorrectly, and now anyone on the internet can retrieve them. No sophisticated malware, no attacker breaking through a firewall, no dramatic exploit, just one configuration mistake exposing sensitive information to people who were never supposed to see it. That is a confidentiality failure. And this is where the CIA Triad becomes useful. Instead of simply saying, "We had a security incident," you can ask, which security objective failed? Why does that failure matter? And what controls could reduce the chance or impact of it happening again? In this example, confidentiality failed because unauthorized people could access sensitive information. The CIA Triad gives you a framework for recognizing that failure, explaining why it matters, and beginning to identify the controls that should address it. That's the model underneath everything we're going to do in this video. By the end of this video, you won't just be able to define confidentiality, integrity, and availability. You'll be able to look at a security incident, identify the security objective most directly affected, and explain why. You'll also understand that real incidents don't always fit neatly into one category. A ransomware attack, for example, may affect availability by making systems inaccessible. It may affect integrity by changing or encrypting data. And if information is stolen before encryption, confidentiality may be affected too. So the goal isn't to force every incident into a single box. The goal is to use the CIA Triad as a framework for understanding what happened. You'll learn how common controls such as encryption, MFA, least privilege, hashing, redundancy, and backups support different security objectives. You'll also see why implementing a control isn't enough. You need to verify that the control is configured correctly, monitored where appropriate, and actually addresses the failure you're trying to prevent. By the end, you'll be able to move from incident, security objective, failure mode, appropriate control. That's a much more useful skill than simply memorizing three definitions. Let's define the three objectives. Confidentiality means information is accessible only to people, systems, or processes that are authorized to access it. Think, who is allowed to see this? Integrity means information remains accurate and trustworthy and is not changed improperly. Think, can I trust that this information is what I expect it to be? Availability means authorized users and systems can access the information or service when they need it. Think, will the system be there when legitimate users need it? These objectives appear directly or indirectly across many security frameworks, audits, architectures, risk discussions, and cybersecurity interviews. But don't treat them as three isolated vocabulary words. Treat them as questions. Who should be able to see the information? How do we know it hasn't been changed improperly? And can legitimate users access it when they need it? Those three questions are much easier to apply to a real security problem than three definitions you memorized for an exam. Here's the mental model I want you to use throughout this video. When something goes wrong, don't start by naming a security product. Start with the incident. Ask, which security objective was primarily affected? Sensitive information was exposed to unauthorized people? Think confidentiality. Financial information was changed without authorization. Think integrity. A critical application became unavailable to legitimate users. Think availability. But remember, real security incidents can affect more than one objective. Imagine ransomware infects a hospital. Systems become unavailable. That's an availability impact. Files are encrypted or otherwise changed without authorization. That's also an integrity impact. And if attackers steal patient information before encrypting the systems, confidentiality is affected too. The CIA Triad isn't asking you to pretend only one of those happened. Instead, ask which security objective was primarily affected in the scenario you're analyzing. Then identify any additional impacts. Once you understand the failure, ask the next question. Why did it happen? Was access too broad? Was authentication too weak? Was data changed without detection? Was there a single point of failure? Was recovery never tested? Now, and only now, ask, what control would meaningfully address that failure? That's the workflow. Incident, security objective. Failure mode, appropriate control. Diagnose first. Choose the control second. Recall time. Imagine a hospital uploads thousands of patient forms to a storage link that anyone on the internet can open. Which CIA pillar failed first? Confidentiality. The information was exposed to people who were not authorized to see it. Now go one step further. What controls could reduce the chance of that happening again? Examples include blocking public access, using least privilege permissions, reviewing access policies, monitoring for public exposure, and classifying sensitive data before it is stored. The goal is not just naming the pillar. The goal is connecting the failure to controls that address the actual scenario. Here's an important lesson. Security controls are not interchangeable. Just because several controls support confidentiality doesn't mean they solve the same problem. Start with encryption. Encryption helps protect information from being read without the appropriate cryptographic key. Now consider multi-factor authentication, or MFA. MFA addresses authentication. It makes it harder for someone to gain access using only a stolen or compromised password. Role-based access control and least privilege solve another problem. They help limit what an authenticated user or system is authorized to access. Someone may successfully sign in and still have no legitimate reason to access payroll records, patient information, or administrative systems. Now consider data classification. Classification identifies how sensitive or important information is, so the organization knows how that information should be handled. Classification by itself doesn't prevent someone from placing a file in the wrong location. Instead, classification can guide handling requirements and drive controls, such as sensitivity labels, access restrictions, data loss prevention, encryption requirements, retention rules, or additional review. Think of classification as answering. How sensitive is this information, and what protections should follow from that? So remember, encryption helps protect the information itself. MFA strengthens authentication. Least privilege and RBAC limit authorized access. Data classification helps determine how information should be handled and protected. All four can support confidentiality, but they address different failure modes. That's why good security analysis doesn't begin with, which security product should we deploy? It begins with, what problem are we actually trying to solve? After you block public access on a storage bucket, do not stop at the confirmation screen. First, verify that anonymous or public requests can no longer retrieve the object. Then test the applications, service identities, and users that legitimately need access. Confirm that they still have only the permissions required for their job. Finally, review the bucket policy, access control settings, and any inherited permissions. The exact screens and labels vary by cloud provider, so follow the current provider documentation for the service you are using. This is the difference between changing a setting and validating a control. You are checking two things at once: confidentiality, because unauthorized users should be blocked; availability, because authorized applications still need to work. For one storage bucket, changing the setting manually in a cloud console may be fine. But what if you have 20 buckets, 200, or thousands of cloud resources across multiple environments? Now you need automation. Most major cloud platforms provide command line tools, APIs, infrastructure as code, and policy capabilities that can help you apply security configurations consistently. The basic workflow is simple. First, discover the resources that should follow the security requirement. Second, identify resources that don't comply. Third, apply or enforce the required configuration. Fourth, verify the result. And finally, monitor for future configuration drift. That last step matters. A script that fixes 20 buckets today doesn't guarantee that someone won't accidentally create a publicly accessible bucket tomorrow. That's why mature environments increasingly move from find it and fix it toward define the secure configuration and continuously enforce or evaluate it. The exact commands and services depend on your cloud provider, so always use the provider's current documentation. But the security principle stays the same. Make the control repeatable, make it testable, and make it difficult for the same mistake to quietly return. Let's connect confidentiality controls to the specific problems they solve. Encryption protects information by making it unreadable without the appropriate cryptographic key. But be precise about what you're protecting. Encryption at rest protects stored data when keys are appropriately managed and access to decryption is controlled. Encryption in transit, such as TLS, protects data while it moves between systems. Encryption does not automatically prevent an authorized application or user from accessing decrypted information. That's why encryption is only one part of confidentiality. MFA addresses a different problem by strengthening authentication. Least privilege and role-based access controls limit what authenticated users or systems are authorized to access. Data classification helps determine how information should be handled and which protections should apply. These controls can work together, but they are not interchangeable. The professional question isn't, do we have encryption? It's, what confidentiality failure are we trying to prevent, and does this control actually address it? Second recall. 6 months after leaving the company, a former employee can still access the billing system. Which CIA objective is immediately at risk? Confidentiality. Someone who is no longer authorized can still access information. Now, what's the missing control? Effective offboarding and access revocation. When someone leaves an organization, disabling the account may be only one step. Active sessions may need to be revoked. Role assignments and privileged access may need to be removed. Group memberships may need to be updated. Application assignments and access to shared resources may need to be terminated. And ownership of files, applications, automation, or other resources may need to be transferred safely. The broader principle is identity lifecycle management. Access should change when someone's relationship with the organization changes. And notice that this isn't only a confidentiality concern. If the former employee can modify billing information, integrity could also be affected. If the account can disable systems or delete critical resources, availability could be affected too. The CIA Triad helps you identify the immediate problem while still considering the larger security impact. Picture a wire transfer file that leaves the finance team as $500. Somewhere between their server and the payment processor, one number changes. The bank pays out $50,500. That is an integrity failure. Not necessarily a hacker, but any unauthorized change. Integrity means data stays accurate and unaltered unless the change was authorized. So accidental edits count, not just attackers. 4 controls can help detect or limit unauthorized changes. Hashing produces a fixed-length fingerprint of a file. If you compare a file's hash to a trusted baseline hash and the values differ, the file has changed. If they match, the file matches that baseline. A matching hash does not prove the file is safe, approved, or free of malware. It confirms equality with the trusted reference you chose. Digital signatures can help verify both integrity and the identity of the signer. When the signature is valid and the signing identity is trusted, you have stronger evidence that the content has not been changed since it was signed. Version control and append-only audit logs make authorized changes visible and easier to investigate. A change may still occur, but the organization can see who made it, when it happened, and what was modified. Finally, immutable backups can help preserve a known good recovery point when ransomware or another destructive event attempts to change or delete data. Each control has a different purpose: compare, authenticate, trace, or recover. Let's actually verify a file's hash in PowerShell. Suppose the file is called patientrecords.csv. Open PowerShell in the folder containing the file and run getfilehash.addPatientRecords.csv algorithm SHA-256. PowerShell calculates the SHA-256 hash and returns a long hexadecimal fingerprint. Now compare that value with a trusted baseline. That trusted value might come from a software vendor, a protected inventory system, or another source you have reason to trust. If the two values match, the file you have now matches that trusted baseline. If the values don't match, the file is different. Maybe someone changed it. Maybe it became corrupted. Maybe it was replaced. Or maybe you're comparing it with a different legitimate version. The mismatch tells you to investigate. And remember one important limitation. A matching hash does not automatically prove that a file is safe, approved, or free of malware. It answers a narrower question. Is the file I have now identical to the trusted version I'm comparing it against? That's why hashing is such a useful integrity control. Here is the flow. Start with an original file from a trusted source and calculate its hash using a strong algorithm such as SHA-256. Store that expected hash somewhere you can trust. For example, in a signed vendor release page, a protected repository, or a trusted inventory system. Later, calculate the hash of the file you have now. Compare the values. If they match, your current file matches the trusted baseline. If they do not match, the file is different from that baseline. It may have been altered, corrupted, replaced, or simply updated. Hashing answers a specific question. Is this file the same as the trusted version I expected? It does not by itself answer every security question about whether the file is safe, authorized, or appropriate to run. Here is the beginner trap. HTTPS and TLS protect the connection while data travels between systems. When the connection is correctly authenticated and functioning normally, TLS helps protect the confidentiality and integrity of data in transit. But that protection applies to the communication channel. It does not create a permanent integrity record for a file after the file has been stored, copied, edited, or moved to another system. Imagine downloading a file over HTTPS. TLS helps prevent someone from silently changing the file while it travels from the server to you. But once that file reaches a server, share, or endpoint, you may still need a trusted hash, digital signature, version history, change control record, or audit trail to know whether it changed later. Use transport security for data in motion. Use integrity controls and trusted baselines for data at rest. Pause for a quick recall check. A digital forensics analyst receives a drive that may contain evidence. Before creating a forensic image, the analyst connects the drive through a write blocker. Which CIA objective does the write blocker directly protect? Integrity. And why? Because the analyst doesn't want their own forensic tools or operating system to accidentally modify the original evidence. Even a small unintended write could raise questions about whether the evidence changed during the investigation. The write blocker helps prevent writes to the original media while allowing the analyst to read the data needed for acquisition. The principle is simple. If evidence may later be used to explain what happened, preserve its integrity from the beginning. Don't just investigate the evidence. Protect your ability to demonstrate that the evidence wasn't improperly changed during the investigation. Here's the part almost everyone gets wrong. An online retailer has a backup. A good one, actually. But when a server dies, the restore takes 2 full days because nobody ever timed it. The site stays down for those 2 full days until the restore completes. That is an availability failure, and it's the pillar most junior techs ignore until revenue stops moving. The next few minutes cover what actually keeps systems up, not just having a backup, but being able to run from it. 5 controls keep availability real. Redundancy means spare capacity, so one failure isn't fatal. Separate locations protect you when a whole site goes down. A standby takeover switches work to a healthy system. Tested recovery tells you how long restore will actually take. And traffic absorption handles a flood that would otherwise exhaust the servers. Now let's think bigger than one failed server. Imagine an application running in Region A. Users normally reach that application through a global traffic management or load balancing layer. Health monitoring continuously checks whether the application environment is responding correctly. Now, Region A experiences a major failure. If the architecture has been designed for regional resiliency, traffic can be redirected toward a healthy application environment in Region B. But redirecting traffic is only one part of the design. The application must also be available in the second region. Required data must be replicated or recoverable. Dependencies must be reachable. Identity and security controls still need to work. And the failover process needs to be tested. Otherwise, the organization may discover during the real outage that its backup region exists only on an architecture diagram. A well-designed failover architecture could turn what might have been hours of downtime into a much shorter disruption. The exact recovery time depends on the architecture, application, data strategy, and recovery objectives. The availability lesson is simple. Redundancy helps. But tested redundancy is what gives you confidence that the second path will actually work when the first one disappears. Here is a better security gut check than simply counting controls. Choose one important system and list its most meaningful failure scenarios. For confidentiality, ask, could unauthorized people access sensitive information? For integrity, ask, could important data be changed without authorization or without a reliable record? For availability, ask, could legitimate users lose access, and could we recover within the time the business requires? Then, identify the controls that address each scenario. Do not just count them. Ask whether they are relevant, properly configured, monitored, tested, and owned. 2 effective tested controls can be stronger than 6 controls that nobody reviews or knows how to operate. Your weakest area is not necessarily the pillar with the fewest control names. It is the scenario where the organization has the most important, unaddressed or untested exposure. A backup is not the same thing as availability. Backups support recovery, and recovery supports availability. But only if the organization can restore the right data within the required time and verify that the restored system works. So run a recovery test. First, document the recovery procedure in a runbook. Second, restore data or a system into a safe test environment. Third, measure the recovery time and compare it to the organization's recovery objective. Fourth, verify the restored data opens correctly, the application functions, and the recovery point contains the information you expected. A backup that has never been tested is an assumption. A tested, documented recovery process is evidence that the organization can restore service after a disruption. Checkpoint. In an operational technology environment, such as a water plant, power facility, or manufacturing site, operators lose access to a critical control system. Which CIA pillar is immediately at risk? Availability, because operators may be unable to see, manage, or safely control the physical process. But use the full picture. In OT and ICS, human safety and operational continuity often receive heightened priority. Confidentiality and integrity still matter too. Incorrect sensor data, unauthorized command changes, or exposed control system details can also create serious safety and operational consequences. The lesson is not that one pillar always matters and the others do not. The lesson is that the impact of each pillar depends on the system and the real-world process it supports. Now we get to the trade-off that security teams eventually learn the hard way. Imagine a company requires a long passphrase, a rotating second factor, and a VPN every time an employee accesses an internal business application. Each control may have a legitimate security purpose. But suppose the combination creates so much friction that employees begin looking for shortcuts. Files get sent through personal email. People copy information into unapproved applications. Support requests increase. And legitimate work slows down. Now the security design has created a new problem. The lesson isn't authentication is bad, and it definitely isn't. Make security weaker so users are happy. The lesson is that controls need to be designed around the actual risk, the sensitivity of the system, and the way legitimate users need to work. A highly sensitive administrative system may justify much stronger access requirements than a low-risk internal information page. And sometimes the answer isn't removing a control. It may be using better technology. Single sign-on. Phishing-resistant authentication. Managed devices. Risk-based access. Or another design that preserves strong security without forcing unnecessary friction into every interaction. Security controls have operational consequences. Good security design considers those consequences before users invent their own workaround. Maximum confidentiality sounds noble. Encrypt everything, lock every permission, force auth everywhere. Maximum availability sounds fast. One login, open access, no friction. But max on either side breaks the other. The real skill is choosing the balance on purpose. A public blog can lean hard toward availability. A patient database leans hard toward confidentiality. Same company, same model, different settings. Before you add a control, run a 3-question pre-flight. Imagine a cloud storage change that makes important files much harder to delete or overwrite. Question 1. Which pillar does that primarily strengthen? Integrity, because it reduces unauthorized or accidental modification and deletion. It may also support availability and recovery by preserving data that the organization may need later. Question 2. Which pillar or operational goal could it make harder? Availability or usability. Legitimate cleanup, updates, or incident response actions may take longer if the control is designed poorly. Question 3. Can the business tolerate that trade-off right now? If yes, implement the control with a clear exception and recovery process. If no, look for a lighter control or a design that protects the data without blocking legitimate work. The goal is not to maximize a control in isolation. The goal is to improve security while preserving the organization's ability to operate. Here's the whole model on one screen. 3 nodes in a loop, not a ladder you climb. A new confidentiality rule can add sign-in friction and hurt availability. A failover choice can change where data lives and create an integrity question. That's not a failure, it's the job. Security is a balance you keep rebalancing, not a setting you set once. The CIA Triad is a useful lens, but major frameworks and assurance programs express security objectives in different ways. NIST Special Publication 853 is a broad, customizable catalog of security and privacy controls. Its controls help organizations manage many types of security and privacy risk, including confidentiality, integrity, availability, authentication, accountability, resilience, and more. ISO IEC 27001 is a standard for building and operating an information security management system. It helps organizations manage information security risk through a structured program of policies, responsibilities, assessment, treatment, and improvement. SOC2 evaluates controls against selected trust services criteria. Those can include security, availability, processing integrity, confidentiality, and privacy. The scope depends on what criteria the organization includes in its report. GDPR Article 32 specifically calls for appropriate technical and organizational measures to support, among other things, the ongoing confidentiality, integrity, availability, and resilience of processing systems and services. You do not need to memorize every clause as a beginner. The practical takeaway is this. Frameworks ask organizations to choose, operate, test, and document controls that address their real risks. CIA is one useful starting point for thinking about those outcomes. Checkpoint. An auditor asks, "How do you know a critical file was not changed?" You answer, "We downloaded it over HTTPS." Is that enough? Not by itself. HTTPS helps protect the confidentiality and integrity of data while it travels over the network. But it does not prove that the file remained unchanged after it was stored, copied, or edited. For integrity at rest, show evidence that fits the stored file scenario. A trusted hash baseline, a valid digital signature, controlled change records, immutable logging, version history, or audit logs. The key distinction is simple. TLS protects the journey. Integrity controls help you verify the destination and the history afterward. Interviewers usually don't need you to recite a giant list of security products. They want evidence that you can connect a security problem to an appropriate response. So when someone asks, "How would you secure sensitive data?" don't immediately answer, "Firewall, encryption, MFA, antivirus, SIEM." Instead, structure your answer around the failure. For example, if unauthorized account access caused a confidentiality failure, I would first determine how that access occurred. If stolen credentials were involved, phishing-resistant MFA could reduce that attack path. If excessive permissions increase the exposure, I would also review least privilege and role assignments. If sensitive information was stored without appropriate protection, encryption and access controls may need to be reviewed. Notice the pattern. Identify the incident or failure. Identify the security objective affected. Identify the root cause or failure mode. Then recommend a control that actually addresses that cause. That's much stronger than listing products. It shows the interviewer that you understand something important. A security control is valuable because of the risk it addresses, not because you happen to know its name. Now let's return to the former employee from our earlier checkpoint. Imagine today is their last day. Changing one role assignment is not enough. Start by following your organization's approved offboarding process. At the appropriate time, disable the account so the former employee can no longer sign in. Then revoke active sessions so previously issued sign-in sessions don't simply continue working. Next, review and remove access that is no longer authorized. That may include administrative or privileged roles, group memberships, application assignments, access to shared resources, delegated permissions, and other entitlements associated with the person's job. Then ask another important question. Does this account own anything? Maybe the user owns an application registration, a shared resource, an automation, a mailbox, a cloud resource, or something another employee will need tomorrow. Those responsibilities may need to be transferred before access is removed. Now consider a different scenario. The employee isn't leaving. They're moving from infrastructure engineering into another department. The same principle applies. Access should change with the job. Remove standing privileges that are no longer required. Keep the permissions needed for the new responsibilities. And where the organization supports it, use time-bound, approval-based privileged access instead of permanent administrator rights. The exact portal labels and technical sequence can change, so always follow your organization's runbook and current platform documentation. But the security principle is stable. Access should reflect what someone is authorized to do now, not the maximum access they accumulated throughout their career. A new help desk technician is given full production administrator access because the team is short-staffed. What is the safer first move? Start with the minimum role needed for the actual task. If elevated access is genuinely required, use an approved, time-bound, auditable process rather than permanent, broad administrator rights. Require appropriate approvals, monitor the privileged activity, and remove the elevated access when the task is finished. The point is not to make new employees unable to work. The point is to give them enough access to do the job without giving one account the power to change everything in production. That is least privilege in practice. Let's lock in what you can actually do now. First, you can look at a security incident and identify which CIA objective was primarily affected. Unauthorized disclosure? Think confidentiality. Unauthorized modification? Think integrity. Legitimate users can't reach the service? Think availability. Second, you can connect controls to the failure they're actually designed to address. Encryption, MFA, least privilege, hashing, digital signatures, logging, redundancy, failover, tested recovery. You're no longer treating those as random security products or technologies. You're asking what problem each one solves. Third, you can recognize trade-offs. A control that improves confidentiality might introduce friction. A control that protects integrity might make legitimate changes harder. An availability design might introduce new complexity or data protection questions. That's the core skill this model is designed to teach. Identify the security objective. Understand the failure. Choose controls that address the real problem. And evaluate what those controls change elsewhere. If you can do that consistently, you're no longer just memorizing the CIA Triad. You're beginning to use it. Your move this week is to review one small system you actually use, such as a shared drive, a personal website, or a home lab virtual machine. Make 3 columns: confidentiality, integrity, and availability. Under each column, write one realistic failure scenario. For confidentiality, could an unauthorized person see the data? For integrity, could the data be changed without authorization or without a reliable record? For availability, could legitimate users lose access, and could I restore the service? Now list the controls that actually address each scenario. For every control, ask 4 questions. Is it configured correctly? Is someone responsible for it? Is it monitored or reviewed? Has it been tested? Do not count the number of controls and call the smallest number your weakest pillar. Look for the scenario where an important failure has no relevant, tested, and usable safeguard. If you want to go deeper, consult the NIST SP 853 control catalog and use a cloud sandbox or home lab to practice safely. Always confirm current trial, free tier, and billing terms before creating resources. Next up, we're going to connect the CIA Triad to 4 concepts you'll use throughout cybersecurity: threats, vulnerabilities, risks, and controls. Consider a phishing attack. An attacker sends an employee a fake login page and tricks the employee into entering a password. What's the threat? The phishing attack and the attacker behind it. What weakness could make the attack more successful? Maybe the organization relies on passwords without stronger authentication. What is the risk? The attacker could gain unauthorized access to company systems or information. And what control could reduce that risk? Phishing-resistant multi-factor authentication could make a stolen password much less useful. But that's where security thinking gets interesting. No single control stops every attack path. So instead of asking, do we have MFA, we're going to learn to ask, what is the threat? What vulnerability or weakness makes this scenario possible? What could happen to the organization? And which controls meaningfully reduce that risk? That's the next step. Before then, Take one practical action. Choose a personal account you own and review its authentication settings. If stronger MFA is available, consider enabling it. Then ask yourself, what attack does this control help prevent? Because that's the habit we're building. Don't just turn security controls on. Understand what they're protecting you from. The CIA Triad is a model you will reuse for years. It gives you 3 foundational questions. Who should be allowed to see this information? How do we know this information is accurate and has not been changed improperly? Can legitimate users access the system and information when they need it? Those questions cover confidentiality, integrity, and availability. But CIA is a foundational lens, not the entire universe of security. Real security decisions also involve objectives such as authentication, authorization, accountability, privacy, safety, resilience, and non-repudiation. Use CIA to identify the primary security outcome at stake. Then use the broader context of the system, the users, the threats, and the business objective to choose the right controls. That is how the model becomes useful, not as 3 words to memorize, but as a disciplined way to start asking the right questions. Remember, careers aren't built by watching videos. They're built by applying what you learn. Pick one thing from today's lesson, build it, document it, and share it. That's how you get hired. Thanks for watching Hired in IT, where we're turning IT knowledge into career opportunities.